Okay, so we're going to start on the nonlinear equations proper now. We're going to do traffic waves. So these are a kind of beautiful example of these nonlinear PDEs that have shock waves. So we're just going to talk a little bit about the problem and then analyze it. So people understood this was kind of probably a bit of a toy problem when they solved it for traffic, and there were fluid mechanicians who wrote this article, and they'd studied gas and other kinds of problems that are more complicated, and this is a simple example they came up with, but it's a great example for teaching, and we can all relate to it as well. So what we've got is we've got a road here with a whole lot of cars on it. Draw some cars whizzing along at this speed. So we're going to use a continuum model for traffic. I'm not a great drawer of a car, am I? All right, there's our car. So what are the variables we've got? We've got rho, that's our key variable, which is the density of cars. Okay, and it is like cars per kilometre, if you like, or something like that, some units. We're going to non-dimensionalise everything anyway. And then we've got v, which is the velocity of the car. And we're going to assume that v is a function of density. Well, that's critical to our analysis. So basically, if the car, as the density of the cars changes, the speed changes. Double check I've got everything working here. Yeah. Okay, so as the density of these cars becomes denser, then the speed changes, the cars slow down. Makes sense, and it doesn't depend on the driver or the time of the week or the amount of rain or anything like that. And then we have Q, which is the flux of cars. So this is the flow of cars. And Q is given by the density of the cars times the velocity. Okay, that's the flow of cars. So basically that means that's the quantity that you're standing here, the little person here, he would observe so many cars passing per minute. Okay, cars passing per minute. Now, almost all of these physical systems, they have two things. They have a conservation law and an equation of state. And then there's an equation of state. So this thing here is an approximation. It depends on the rain, it depends on the type of drivers, it depends on the country. You know, people in Germany drive a lot faster than here, or vice versa. People in Australia don't, I don't know. You know, this is approximate. That's sort of a modelling question. And this thing here is always true. Or more or less always true, okay, as long as the cars don't crash. And this conservation state is conservation of cars. A car is not created or destroyed. I'm missing the B here. Conservation of cars. All right. Cars are not created or destroyed. So what does that mean here? Let's just try and work out what it means for conservation of cars. And this is this is lots and lots of equations. You know, atoms are conserved. So we have conservation of mass or something like that. This is very similar to the conservation of mass argument. So what we do is we have a stretch of road here, we have a position x, and we have x plus delta x. So we have a flow of cars coming in. So the in is the flux, Q of x. And going out is Q of x plus delta t. Oh, sorry, delta x. All right. So you might think, well, flow in equals flow out, but actually cars can accumulate in here. That's the whole point. So this thing here, the number of cars in here is equal to the integral from x to x plus delta x of the density of cars. Right? Well, that's the total number of cars in the interval. You integrate the density and you get the number of cars. So the conservation law says that the rate of change, d by dt, of this quantity, the number of cars in this interval, this makes perfect sense, it has to be true, equals the flow in minus the flow out. So it equals q of x minus q of x plus delta x. Okay, now then we take the limit as delta x goes to 0. So what's going to happen here? So this integral here is going to become the time derivative of delta x times rho of x on the t, right? If you think about that, this is going to be approximately a constant here. And then we can take the delta x over the thing here, and we get the time derivative of rho equals q of x minus q of x plus delta x divided by delta x. So that gives us the time derivative of the density is equal to the x minus the x derivative of q. And that's the conservation law. That must be true, basically. Otherwise, I mean, cars are crashing or driving off the side of the road or disappearing by aliens or sucking them out or something like that. Other than that, that equation has to be true. And we normally write it as d rho dx, dt plus dq dx equals 0. Okay, so equivalently.